Hello friends, in the last lecture we discussed the derivation of radiative heat transfer equation. We discussed how the radiation is attenuated as it passes through a participating media. It is subjected to scattering, absorption. It is also subjected to augmentation by emission and in scattering. The governing equation that we derived had 7 parameters including time, and if we assume quasi steady problem and ignore the time coordinate, the total number of parameters will be equal to 6. So, the equation is basically an integral differential equation and in itself is extremely difficult to solve. So, in this lecture we will see how we can solve this problem. Normally we do lot of simplifications while solving these type of problems. There are two approaches. In first approach we take the exact problem, but we derive an approximate solution method, and in the second approach we make a simplified approach and try to solve this simplified problem using some exact method. So, there are large number of methods that have been developed to solve the radiative transfer equations. We have exact methods for very simplified geometry, for example plane parallel slab, which is a one dimensional problem, and similarly in cylindrical and spherical coordinates. One such problem we solved in the previous lecture to find out the intensity of radiation coming out of an isothermal sphere. In this lecture we will discuss the exact solution in plane parallel medium. For problems having higher dimensionality and higher complexity, we have approximate solution methods such as spherical harmonics P1 method, the discrete ordinate method, the finite volume method, and the discrete transfer method. So, these are some of the major methods, major approximate methods that are used to solve radiative transfer equation in higher dimensions or complex geometries. Then based on the energy balance, similar to what we discussed in the case of energy transfer between parallel plates, we have some methods which solve radiative transfer equation, not exactly the radiative transfer equation, but rather the radiation problem in participating media. We have the zone method, the imaginary plane method, the Monte Carlo method. These methods solve radiative transfer problem in participating media without actually solving the radiative transfer equation. So, these are basically the energy balance method which directly or indirectly rely on the view factor or exchange areas. So, we will discuss as we go along these type of methods also. The focus of this presentation, this lecture is the solution, exact method solution in plane parallel media. So, plane parallel media is basically a medium which is one dimensional. So, we have one dimensional medium, two parallel plates. The thickness of the plates in the plane of the board is infinite, and the length of the plates or the width of the plates is also infinite. So, there is only one finite dimension, which is the separation distance between the two plates. So, for this plate, for this configuration, the solution is relatively simple. We can solve the equation of radiative transfer RTE. So, recalling from the previous lecture, the RTE is given by d I lambda upon d tau lambda. So, this is in non-dimensional optical thickness. So, the denominator tau lambda is in non-dimensional form, tau lambda is spectral optical thickness. So, the equation is d I lambda by d tau lambda is equal to 1 minus omega lambda. Omega lambda was single scattering albedo, IB lambda the spectral blackbody emissive power minus I lambda plus omega lambda upon 4 pi, and then this integration this results from the scattering in scattering. So, phi lambda is the scattering phase function, and in such form, this equation is basically an integral differential equation. On the left hand side have a differential and the right hand side has an integration. So, we call it an integral differential equation, and it is very difficult to solve. Now, we have 6 coordinates or 6 parameters, independent parameters here. The 3 parameters are the spatial coordinates x, y and z, and we see that as an engineer we are used to solving the partial differential equation in 3 dimensional space. So, x, y, z is not an issue as far as this equation solution of this equation is concerned. The one other parameter is the wavelength. Now, we will solve this problem for a single wavelength and then we will integrate over all the wavelengths. So, the calculation of this radiative transfer equation or the solution of this radiative transfer equation is not as such complicated by spectral variable lambda. The lambda makes the solution expensive, that means we have to solve the solution the equation for a large number of wavelengths and then find the sum. So, the solution is expensive, it takes time to solve the problem for all the wavelengths, but as such for each wavelength the problem is independent and wavelength does not create as much complexity into the solution of the problem as is basically introduced by the 2 directional variables theta and psi, the polar angle and the azimuthal angle. So, the major complication in the solution of this equation comes from the directional dependence of intensity. This directional dependence of intensity also appears in the integral part of this equation, that is the right hand side, the last term. The scattering phase function introduces how the intensity will be redistributed after scattering. So, that is basically a directional quantity, and similarly this particular governing equation is for a given path and we have to integrate this equation to find out radiative heat flux and divergence of heat flux over all the solid angles. So, the major complication in the solution of this equation comes from or it arises from the dependence on theta and psi, that is the directional dependence of intensity. So, if somehow we can simplify the solution or the dependence of this intensity on theta and psi, if this relationship can be simplified by either assuming that I does not depend on psi or I does not depend on theta or I does not depend on any of the parameters, the problem can be simplified significantly. So, we will see how this relationship can be simplified for some standard geometry. The problem that we are going to discuss is a plane parallel medium. So, plane parallel medium, as I explained, it has infinite depth into the board plane of the board, and the width of the plates is also infinite. So, this is called one dimensional slab. Now, the 2 plates that bounds this medium are isothermal and isotropic, that means anywhere on the plate the properties are same, that means emittance of the surface is not a function of the x coordinate, okay, that is it is isotropic. So, plates are isotropic, the emittance also is isotropic, it does not depend on the location, it also does not depend on angle. So, we have diffuse surface. So, when we assume that, then we can say in this configuration the intensity will be a function of theta and z only. Okay. So, intensity is a function of z and theta only, and it does not depend on any coordinate like x, y and psi. So, so intensity is not a function of these variables. Okay. So, it depends on only 2 parameters theta and z, and with this we can simplify the problem significantly. The space, the medium between the 2 plates is filled with a gas with absorption coefficient kappa. So, this space is filled with the gas with absorption coefficient, let us say kappa lambda. The spectral absorption coefficient is kappa lambda and it is uniform. The temperature of the medium is also uniform, but it may vary in the direction, in the z direction. So, temperature as well as kappa lambda, that is absorption coefficient, is a function of z only. Okay. So, it is a plane parallel medium, there is no dependence on x coordinate. So, T and kappa lambda, the absorption coefficient and temperature are function of z only. Okay. And under this assumption, the intensity is going to be a function of z and theta only. So, now understanding the two images that are shown here, at any point P we are basically interested in finding the intensity. So, we have to find out the intensity at any point P. Now, point P is suspended in space, it will receive radiation over the entire solid angle 4 pi. So, we divide this solid angle 4 pi into two parts, one radiation coming from below, that is from the bottom plate and the gas between point P and the bottom surface, and second part of the intensity that reaches point P is basically from the medium and surface above point P, that is the top plate and the medium between it. So, we have divided the problem into two parts. Okay. In the first part, the intensity originate from the point on the surface 1, okay, towards point P, it undergoes emission. So, from here to here it undergoes emission from the medium, it also has contribution from radiation emitted by the surface. So, it undergoes all the four processes: attenuation by absorption and scattering, and augmentation by inscattering and emission. Now, we use the coordinate system. So, starting from the point of origin of the ray, we use coordinate tau s and tau to represent the position of any point between the origin and point P. So, any point on this, let us say Q, has location or optical path length as tau s prime, and the optical path length of point P has value of tau s. So, this is tau s is basically the optical path from the point of origin of the ray to point P, that means kappa times s, and tau s prime is any point on this ray, let us say q s, kappa times s prime. So, that is the path length of point q s, and this is along the ray. Now, along the normal direction we have a coordinate system tau and tau prime. So, tau is basically the optical distance of P from the plate, the vertical distance from vertical optical distance from the plate. So, this is the distance tau, non-dimensional distance, optical distance tau, and similarly the coordinate or the distance of point Q will be z, tau prime. Okay. And same thing we can have for the intensity coming from the upper side. So, we represent the coordinates in a similar fashion. The only thing is now the coordinate of this point P will be tau L minus tau, where tau L is the total distance of the plate. So, this distance, let us say total distance is L. So, tau L is simply kappa times L. Okay. So, this is basically the notation. One last thing in the notation, the intensity that originates from the bottom surface and moves in the upward direction is represented by I plus, it is a function of tau and theta, and the intensity that comes from the top surface and moves in the downward direction is represented by I minus, and it is a function of tau and theta. So, we start we have to solve for these two intensities I plus and I minus, and then use these two intensity to find out the quantities of our interest, that is the radiative heat flux and divergence of heat flux. So, these two quantities are of our interest. So, we start with this radiative transfer equation in non-dimensional optical coordinate, because this is given in optical path along the radiation travel. We have to now change the variables in our coordinate system, that is z and theta. Okay. So, we apply the chain rule. So, d by ds is equal to partial derivative with respect to z, dz by ds, then partial derivative with respect to theta, del theta by ds, plus partial derivative with respect to the azimuthal angle psi, d psi by ds. So, we applied the chain rule. Now, there is no dependence on psi. So, the last term in this will be equal to 0. Now, d theta by ds, d theta by ds is basically the variation of theta in the s direction, and if you will look at it, along this direction the theta is not going to change. So, theta is constant. So, d theta by ds is also equal to 0. Okay. So, this quantity is also 0. So, we are left with, this will become del by del z, dz by ds. Now, dz by ds is nothing but cos theta. Okay. So, dz by ds from this you can see this is dz and this is ds and this is theta. So, dz by ds is simply cos theta. We will represent cos theta by mu. Just for notation purpose, we have introduced a variable mu which is equal to cos theta. Now, our d by ds has become equal to mu times d by dz, because other partial derivatives are not there. So, we have changed the variables. Now, we will simplify our radiative transfer equation. So, from here, from this equation, now we have changed the variable from tau s. Okay. This was in s direction. So, this radiative transfer equation was in s direction. Now, we have changed the coordinates. So, this will be in tau or z direction. So, we have changed the radiative transfer equation in terms of coordinates, where now d tau is simply kappa times z. So, tau is nothing but kappa times z. Okay. So, this is the vertical optical path length. Okay. And the right hand side 1 minus omega I b minus I and plus omega upon 4 pi. Now, I have also changed the intensity in terms of writing of the path length S I. I have written the intensity which is now a function of z and theta. So, z dependence comes in tau and theta dependence comes in mu I. Okay. And we have to integrate over all the solid angles d omega I. One thing you should note is that I have dropped the subscript lambda, and the reason is just for simplification purpose, but the equation is basically valid for each wavelength. Just for convenience we have dropped lambda, but it is understood that the equation is valid for each and every wavelength. Now, mu di by d lambda is equal to 1 minus omega I omega into I b minus I, and removing the azimuthal angle or integrating over the azimuthal angle. So, d omega we know is basically sin theta d theta d psi. So, we have already integrated over d psi, there is no dependence of intensity on psi. So, we can take it out and the equation is simplified to the right hand side simplifies to omega by 2 integration from minus 1 to 1 I tau mu I d mu I. So, we have to integrate over all the solid all the theta direction. So, this was the simplification of radiative transfer equation. Before we solve this equation formally, let us have a look at the boundary condition. At the bottom boundary, that is z is equal to 0. So, this is my bottom boundary. We assume, let us say it is black, that means epsilon is equal to 1, then the intensity is going to be isotropic, uniform in all direction. So, this is going to be the intensity. So, our I plus, that is intensity in vertical direction, that is moving up at tau is equal to 0 and theta is equal to mu, is simply I b. There is no dependence on theta at the wall. So, intensity is isotropic, and similarly at the top wall also. So, this is I b at local temperature, let us call T 1, and this is I b at local temperature T 2, and this is the plate, the top plate, and the intensity is going to be isotropic, that is uniform in all direction. Now, if our plates are not black, then the intensity or the boundary condition will not be simply the algebraic equation I plus is equal to I b or I minus is equal to I b, then it will be an integral equation, and we have already discussed this in length. Heat transfer from surfaces is governed by Helmholtz kind of Fredholm kind of equation if the plates are gray. So, so same thing we will have. So, I plus now at the surface, the bottom surface in any direction, mu is going to be a function of mu, will be black body emissive power epsilon I b, and the refracted part. So, this is the emitted. Now, it has two components, emitted part and reflected part, and it is in this reflected part we have the integration over all the solid angles. We have taken minus mu. Why? Because the reflected radiation basically includes radiation coming from outside and then reflecting back. So, we are taking mu in the negative direction, that is downward moving mu, downward moving direction for the reflection part, and same thing we do on the top surface. On the top surface, this is the top surface, radiation moves in the upward direction. So, we take positive value here I plus, and then it is reflected back. Okay. So, we see that for gray surfaces, for a medium bounded by gray surfaces, the result is going to be little more complicated than the case where the surface is where the medium is bounded by black walls. Now, we will solve. So, this is our equation. Let us call the first and third term combined as source term. To simplify our notations, we just write I 1 minus omega I b, which is augmentation by emission, and the last term which is augmentation by scattering. So, these two augmentation term we put as S tau, the scattering term. Now, I b is also not a function of mu, and this scattering term is also not a function of outgoing direction. So, we have basically S as a function of tau only, and this is only for isotropic scattering. Okay. So, this is valid only for isotropic scattering, that is we are scattering phase function which is function of mu I, and mu is simply equal to 1. That means, there is no dependence on outgoing direction. Otherwise, if it is not isotropic scattering, then the source function will be a function of tau and mu, but because the scattering is isotropic, the source function is just a function of tau and it does not depend on mu. So, the equation in simplified notation is mu d I by d tau is equal to minus I plus S tau, where S tau is the source term that includes emission augmentation and scattering augmentation. Now, to solve this equation, this differential equation, we will use the approach by multiplying by the integrating factor. So, the integrating factor we have taken is the integrating factor is equal to e power tau by mu. So, with this integrating factor we multiply, and we see that the differential equation is transformed to the form here, d e tau by mu I over d tau is equal to 1 by mu e tau by mu S tau, and we can split this intensity, as I said, in two parts, I plus and I minus. I plus is intensity moving upward and I minus is intensity moving downwards. So, we just are interested in finding the solution of I plus and I minus separately. So, I have written I as I plus as a function of tau and mu, and when we integrate this we get this solution. So, this is the solution of the differential equation that we multiplied by the integrating factor. So, E tau by mu I plus minus E naught by mu, where tau is equal to 0 has been substituted, that means at the bottom wall. So, tau is equal to 0 at bottom wall and I plus 0 mu is the boundary condition. So, we have substituted the boundary condition here, is equal to 1 by mu 0 to tau E tau prime by mu S tau prime. So, we have to take the integration of source term in all directions. So, E tau prime by mu S tau prime d tau prime. So, all the directions we have to basically include, and we have to integrate from 0 to tau, and then if we simplified it, we divide by E tau by mu both left hand right hand side, we get I plus tau by mu is equal to I plus 0 mu, that is the boundary condition. E minus tau by mu is equal minus 1 by mu 0 to tau E minus tau prime by mu S tau prime. So, this is the solution of equation of radiative transfer for any wave starting from bottom surface and moving in upward direction at an angle theta, where cos theta is equal to mu and this distance is tau. So, at this point P, the intensity I plus moving in the upward direction at an angle theta, the distance of this point P from the plate is tau, the intensity is given by this result. Okay. So, similarly on point P, any radiation travelling from the upward plate, the top plate at an angle theta, it will be moving in downward direction, the intensity I minus tau and mu will be equal to I minus tau L mu, that is the boundary condition at this point, E minus tau L minus tau over mu plus 1 by mu, and this integrated over the source term. So, this is the equation of intensity in the two directions at point P, in the upward direction and in the downward direction. Now, we have to find out the expression of radiative heat flux. So, once we know how the intensity is distributed, finding the expression for heat flux is very simple. So, we have to integrate over all the solid angles and multiply by cos theta. So, we remember that Q is basically intensity dotted with normal vector and integrated over the entire solid angle 4 pi. So, that is the expression for heat flux. So, that is what we have done. For n dot s we have multiplied by cos theta, and then solid angle d omega is sin theta d psi. If we write in terms of mu, that is cos theta is equal to mu, it will become simply 2 pi integration from minus 1 to 1 I times mu d mu. Okay. Substitute the value. Now, we can split this integral into I plus and I minus. So, I plus will be the value from 0 to 1 and I minus value will be minus 1 to 0. Okay. So, after substituting the expression for I plus and I minus in this equation, the final solution for heat flux is basically 2 pi, then integration over the I plus, similarly integration over I minus, and the two source terms. These are the two source terms, one term for each I plus and I minus. So, the solution for this plane parallel plate configuration has been found analytically in this form, although there are still some integration that are appearing here, especially the integral in the source term e to the power minus tau prime. So, these integration have to be found before we actually have a closed form solution. Similarly, the incident radiation g tau can be calculated, and we know that we have to find out the value of g before we can solve for the divergence of heat flux del dot q, because the expression for del dot q is simply equal to kappa times 4 pi IB minus G, and the expression of G can be derived in a similar fashion. We define G as 4 pi integrated over solid angles simply I times d omega. Okay. So, this is the expression for the incident radiation, that is intensity integrated over all solid angles, and we get the same or similar result, except we have a mu in the denominator here, and instead of minus sign we have a plus sign here. So, the expression of the Q and G, they are pretty much very similar to each other. Now, so as I said, the solution is complete as of now. The only unknowns now left in this solution are basically the integration that are appearing in these terms, especially the integration of this exponential term that we have to find out. So, now every time we solve this problem, it is very difficult to calculate these integrals. So, researchers, mathematicians have evaluated this integral. In fact, these integrals are very popular. In radiative heat transfer, we call it exponential integrals, and they are very popular. They have been pre-calculated and tabulated in books. So, we define exponential integral E n x as equal to integration from 1 to infinity E minus x t dt upon t power n, where t is a dummy variable here in the integration. So, this is called exponential integral of order n in variable x. So, E n x is exponential integral of order n in variable x. We can use another dummy variable mu. So, by just substituting t as equal to 1 by mu, we get this definition of exponential integral, which is very similar to what we have found in our results. So, we see that 0 to 1 exponential term, and we can relate this exponential integral to the solution of radiative transfer equation. Now, the advantage of tabulating this integration is that we can very easily solve the problems analytically. Exponential integral is very powerful. It has a lot of properties that can be exploited. For example, the derivative property, d derivative of this exponential integral is minus exponential integral 1 order less than the exponential integral E n x, that is E n minus 1 x. Similarly, we can integrate this exponential integral, we get an order higher exponential integral. The first or 0 order exponential integral is E minus x over x. Then there is a property E n plus 1 x is equal to 1 upon n E minus x E n x. So, many times when you solve radiative transfer equation, this type of integration will appear in the solution, and to simplify this, some of these properties can be called and we can find out the solution. As I said, these integrals are tabulated for different values of x. I have given a truncated table. This table is taken from radiative heat transfer MF Modest. So, up to 4th order exponential integral have been given. So, E1 is exponential integral of order 1, E2 second order, third order and fourth order, and so on. So, this table is available in the textbook, at the back of the textbook, and can be used to solve the radiative transfer equation. Now, there are some special cases, especially there are two types of special cases in this problem. One is radiative equilibrium problem and one is specified temperature. In many applications, the temperature is known and you can solve radiation problem straightforward because you know the temperature, but in many applications the temperature is not known. For example, if you are trying to solve for a furnace, a boiler, where we do not know how much temperature exists at different locations in the boiler. So, that problem can be solved using radiative equilibrium problem, assuming conduction and convection are negligible and the temperature in the furnace is mainly governed by radiative energy balance. So, the analysis basically remains the same. In this simplified case, special case, we assume that there is no scattering. That means the intensity, the source function is simply IB. So, S tau is simply IB tau, if we have no scattering, the source function depends on only black body emission power. The walls are black, so I plus is IB1, I minus is IB2. When we assume that, then I plus and I minus solution which we have already calculated earlier can be simplified by substituting for IB1 and IB2 and IB in terms of source term. So, let me just show you the I plus expression we derived earlier. So, this was the I plus expression, here I plus 0 mu was the boundary condition. So, we have substituted the value of intensity at the wall at the boundary in terms of black body intensity IB1 and IB2 to simplify the solution, and same thing we have done for the source term, where we have substituted S tau is equal to IB tau, and our expression for incident radiation and radiative heat flux have also simplified. This is the final solution, where we have now replaced the integrations with exponential integrals. So, the heat flux is simply equal to IB1 third order exponential integral at tau, IB2 third order exponential integral tau L minus tau, and then integration from 0 to tau of black body intensity multiplied by second order exponential integral minus black body intensity and second order exponential integrals. And this problem now is very simple. Of course, if you do not know the quantities like temperature, then it becomes difficult to solve by hand, but you can easily program them. Now, radiative equilibrium means del dot q is equal to 0 or kappa times 4 pi IB minus 0, and this gives you G is equal to 4 sigma T4. So, if you have solved for G using this expression, then you can calculate the temperature, unknown temperature T. So, we substitute G is equal to 4 sigma T to the power 4, and then IB is sigma T1 power 4, IB2 is sigma T to the power 4, and then this is the source term. Again, this is an integral differential equation, and you have to apply this is an integral equation, a Fredholm equation, and you have to apply the algorithms that we have discussed earlier to solve this equation. So, if the temperature field is not known, radiative equilibrium exists, then the solution of the radiative transfer equation is basically an integral equation or the Fredholm equation, which you have to solve using appropriate numerical procedure. On the other hand, so here is the solution. So, I have not solved this, I have taken the solution from the book Radiative Heat Transfer by M. F. Modest. We have written the non-dimensional temperature or emissive power T power 4 minus T2 power 4 divided by T1 power 4 minus T2 power 4. This is non-dimensional emissive power at any location tau, and this is non-dimensional heat flux at any location tau, and we see that almost the variation is linear. So, we see that the temperature variation between the plates. So, we have a top plate and we have a bottom plate. This is at temperature T2, this is at temperature T1. So, we are finding the temperature at some point in the middle or at location tau, this is tau. So, the emissive power or the fourth power temperature variation is linear. Okay. If we have this linear variation in emissive power, it is easy to solve for temperature, you have to just find out power 1 by 4, okay. But the emissive power is linearly varying, and we see that there is a jump in temperature at the wall. Here non-dimensional temperature at the wall is 1, here the non-dimensional temperature at the wall is 0, and there is a jump in that non-dimensional emissive power. So, there is a jump, okay, and this jump basically decreases when we increase the value of optical thickness tau L. So, if you have more absorption, that is kappa is large, then the jump at the wall, the temperature or the emissive power jump at the wall is going to decrease, okay. But for optically thin medium, the jump is going to be significantly large. So, the wall is going to emit much more than the medium. So, jump means there is more emissive power from the wall than the medium, and this difference is going to decrease as we move towards optically thick case. In fact, if kappa tends to infinity, that is optically extreme case, very large optical depth, then the two will be basically same, and the intensity or the heat flux Q will basically tends to sigma T power 4. There will be very little difference in the temperature in that case, and the intensity or the flux leaving the enclosure will be equal to black body emission power for extreme case of optical thickness. Same thing we can do for non-scattering gray enclosure. For non-scattering enclosure, so for the black enclosure non-scattering, we have intensity IB1 and IB2. If we have gray enclosure, the IB1 and IB2 will be just replaced by the radiosity J1, J2, rest of the things will remain same, and we can write down the emissive power, non-dimensional emissive power and non-dimensional heat flux in terms of black surface emissive power phi b. So, phi b is emissive power or non-dimensional emissive power if the surfaces were black, and psi b is non-dimensional heat flux if the surfaces were black. So, in these two variables we can find out the non-dimensional emissive power and non-dimensional heat flux. If the temperature is known, so that was the case when the temperature was not known and we assume radiative equilibrium, like the furnace example. So, the solution becomes difficult due to the involvement of integral equation, but if the temperature is known, then directly we can solve for heat flux using this equation, and we can solve for incident radiation G directly using this integration, and the solution is relatively simple. We can directly solve for it, and the good thing is in many problems the solution is iterative. Even in furnace problem, what we do is we assume that the temperature is known, find out the heat flux and divergence of heat flux, satisfy the overall energy balance. If the overall energy balance is not satisfied, we increase or decrease the temperature. So, in practice or in numerical procedures, the solution is always iterative. So, we do not have to assume radiative equilibrium. So, that solution we do not have to do. In practice, what we can do is we assume that the temperature is known, although that temperature may be a guess temperature, it may not be actual temperature. You satisfy the overall energy balance equation. If the energy balance equation is not satisfied, you correct your temperature and then again solve the radiative problem using the equations given on this slide. That is, you do a forward calculation with temperature known, all these terms you can solve for Q and G, and then you can find out del dot Q, satisfy the overall energy equation, and if not satisfied, correct the temperature. So, thank you. In this lecture we have discussed the solution of plane parallel medium. In the next lecture I will take one example of this type of problem, the plane parallel slab, and try to solve for a simple case. We will also develop solution for one dimensional cylindrical media, the exact method for one dimensional cylindrical media by simplifying the radiative transfer equation in cylindrical coordinates. Thank you.